So for the shifter component in project part A, while the lab write-up doesn't necessarily describe it in detail, there's certainly a multitude of ways one could implement a shifter. Some that will only work in ModelSim, others that would also synthesize nicely. Our needs for the MIPS processors are pretty specific. We need a 32-bit shifter that can operate entirely in combinational logic. It'd be very easy to build a serial shifter that takes up to 32 cycles to do all the shifting. We need to do that all entirely in combinational logic. And the type of shifter that is the most straightforward to implement given those requirements is referred to as a barrel shifter. And it's not something the textbook really talks about at all. And so I'd like to take a couple minutes and just describe how I would go about breaking down the barrel shifter and implementing it structurally. Conceptually, if we want to just draw what it looks like, it has input A, which would be your 32-bit input, corresponding to the value to be shifted, and output, we'll call it F, also 32 bits, which is the shifted amount, and then and we've seen the breakdown in the instruction field itself, that 5-bit shift amount. And 5 bits are sufficient, right? 5 bits allows us to encode a value between 0 and 31, and there's no reason to shift any more than that, right? We have a 32-bit value. There'd be no purpose in shifting 73 bits, right? You'd be shifting in all zeros at that point. Um, so my approach to the shifter is just to break it down bit by bit versus trying to implement it all at once. And that's what you get when you try to design a barrel shifter. In fact, we can look at that shift amount and actually break down the 5 bits of shift and treat them as independent of each other. So if these are our 5 bits of shift, I'm just going to label them as SH 4, 3, 2, 1, and 0. Those are the 5 bits of the shift amount. Which we can actually treat as control inputs to different shifters that we can then concatenate together to get a total of that 5 bits of shift. Let's imagine, as we look at just the first bit, shift amount of 0, what would our design look like? What would be one way to implement just a single bit shifter, right? This would be just for a single bit of control, a binary shifter. It takes a 32-bit input and it shifts it either 1 bit to the left or not at all. Well, how would you implement that? You can think of it in terms of behavioral logic that would make sense to you, but if we think of it in terms of components and functional units and how we would lay them out, you can think of that 1 bit shift as being basically a mux, right? Should my output be the same as the input, so shifting 0, or should it be the value shifted over by 1? A mux allows us to do that, right? We have our if statement. If the shift amount is high, then provide the shifted input, otherwise don't provide me with the original input. We can draw some of that. We won't be able to draw all 32 bits and have that make sense here. But if we have our input I sub A, or I underscore A, and we have the individual bits for it, we could visualize each of those bits connected to a series of independent muxes. Let's just draw 3 of them for now because this is going to take a while otherwise. In which we have inputs 0 and 1 corresponding to a shift amount being set as 0 or a shift amount being set as 1. Let's do the ellipses here to indicate that that would be bit 31. This is bit 0 and bit 1, in which if we don't want to shift at all, then we would just be able to take that input directly and connect that to become our output. Likewise, for the next bit, for bit I underscore A of 1, if the shift amount is 0, we would want that to become our output bit for F. And then finally, dot, dot, dot for our most significant bit. If shift amount is 0, for just that single bit of shift amount, we shouldn't do anything. We should just take our input as output, right? You can do a shift amount. You can do a shift left logical with a 0 shift amount. That's fine. It doesn't change the input at all, but it's a valid way to consider it. Whereas if we actually do want to do the shifting by 1, and we're assuming we're shifting to the left here, the operation is exactly the same if we're shifting to the right. We just have to sort of flip the inputs and outputs around. If we're shifting to the left by 1, then that value should be connected there, right? Instead of 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 1 being IA of 1, it would just be IA of 0 because we've moved those bits over by 1. Likewise, although we can't draw the long arrow over, the other input to this would be I underscore A of 30. And everything would just be over by 1 if we're doing this single bit of shifter. Now we're left with what happens to the least significant bit. Well, what happens, it depends on what shift operator we're doing. For a shift left logical, and we look at the ISA description of what's happening with a logical left shift, we're shifting in zeros. So in that case, it becomes pretty easy to input this part, that there's no other signal we have to worry about. It would just literally be a hard-coded 0. And that would be our single bit shift. And if that's what all you were required to do, you would actually be done. And we take that as our starting point. So that's sort of the first layer of our barrel shifter, that it allows us to shift a single bit. The other observation that allows us to be a tractable design to build in a relatively short period of time is understanding that the shifts can be thought of as being independent of each other. So if we have an operator in which we were required to do a shift left logical by, say, 7, it turns out, and you can work the math out yourself if you don't believe me, that a shift left logical by 7 is the same as shifting to left logical by 4, a result that has been shifted left logical by 2, and let's put this in parentheses as if it's a function call. Shifting left something to the 7 places is the same as shifting a value by 4, shifted to the left by 2, and then shifted to the left by 1. They're additive in that way. And it makes sense, right? To shift something 7 places to the left, we can do so by first shifting it 4 to the left, then shifting it 2 more to the left, then shifting it 1 more to the left. And they add up. So 4 plus 2 plus 1 gives us 7. We get the equivalent amount of shifts by doing it as several stages of shifts. So that holds for all of those 5-bit values. So we can treat those shifts as entirely independent. We have now built a 1-bit shifter, and so the next stage would just be to build a 2-bit shifter. In which similar things are happening. We can still have control bits for that mux of 0 and 1. Instead of shift amount of 0, it's now shift amount sub 1 here. If we're not shifting at all, we would still take IA of 0. And if it's a shift amount of 2 now, we would certainly shift in 0. The same would now be the case for that next bit. This is IA of 1 normally, but if we're shifting to 2, shifting to left by 2, then we should also be shifting in a 0 there. And now likewise for our most significant bit, if we're not shifting at all, that should be IA of 31. And if we are shifting, it shouldn't be IA of 30, now it should be IA of 29. That's a shift left by 2 operator. It either shifts not at all, or it shifts everything 2 bits over to the left. And because these shifts are entirely additive, if we want to shift to the left by 3, for example, we can take the output of that 1 shifter and just connect it directly to the input of that 2 shifter. And that's what you'll be doing when you build your barrel shifter. Literally, what we called OF isn't actually this OF. That's the intermediate result of having potentially shifted 1 bit to the left or not. And we can connect that directly into the input. Right? And VHDL allows us to wire our signals accordingly into the input of our next level of shifter. And you would just do the same. That's a 1 shifter and a 2 shifter. You'd also build a 4 shifter, an 8 shifter, and a 16 shifter, and then you would be done. Ultimately, yeah, you're going to potentially be shifting in a lot of zeros here, but that's the case. If you shift left logical by 31, you've replaced the entirety of the value by those zeros that you have there. And the rest is just details. So that's for a left shift. If it's a right shift, it's the same thing, just with the inputs flipped around. Because left and right are arbitrary, right? Is it 31 down to 0, or is it 0 to 31? It's just a direction you pick to label your wires. Likewise, arithmetic shifts versus logical shifts aren't so bad either. We just have to be careful. Instead of always knowing that we're shifting in constant, maybe it's the sign bit that we're shifting in. But it's the same concept of this barrel shifter, of these 5 stages of shifts happening. I think if you start with this diagram, and label your signals carefully, this isn't going to be too bad. Um, we have to be careful. We can call the ports on our mux something, but the internal signals have to have clear and unambiguous labels to them so we don't inadvertently have multiple drivers in our design. Good luck with the barrel shifter. You should be able to work on this in parallel with other group members working on the 32-bit ALU, but be there for each other. Be there to help each other out in terms of best practices, in terms of looking over each other's code, and I don't think you'll have any trouble with project part A. Good luck.